Hello, everyone. This is from days to minutes, from minutes to milliseconds with SQLAlchemy by Leo. If we have time at the end of the presentation, there are two microphones right in the middle of this corridor right here. If you have any questions, please form a line, and we'll take questions one by one from there. Thank you. Leo.
Thank you. So, I'm here to talk about ORMs. I'm Leonardo, or Leo. I'm a technical lead at Geru, which is a financial services company in Brazil. I'm by no means an expert in either SQL or SQLAlchemy or ORMs. But I like to pass on some lessons I learned while optimizing some really little processes we found out while using SQLAlchemy, in particular the ORM. So Geru, as I said, is a Brazilian fintech. We do loans without collateral, completely online. You don't have to visit the bank or anything like that. Our backend stack is pretty much all Python. We use mostly Postgres for storage. We use Pyramid as a Python framework for almost all our projects. And since we're doing Postgres with Pyramid, SQLAlchemy is a nice fit. There's a really great integration with Pyramid that integrates the request cycle of the web framework with the transaction, with the SQLAlchemy transaction, so it's really nice. Of course, when you talk about SQLAlchemy, there are two aspects. One is the expression language, which is just a fancy way of writing SQL using Python. And then there's the ORM, the Object Relational Mapper, which is where you get classes mapping to tables and records of these tables mapping to instances of the class. In SQLAlchemy, the ORM is built upon the SQLAlchemy DSL, the SQL DSL, but you mostly can use them without, you can use one without ever thinking about the other. And I really like SQLAlchemy. I think it's awesome. But as Martin Fowler said, frameworks still require you to make decisions about how to use them, and knowing the underlying patterns is essential if you're to make wise choices. So we're going to talk about the ORM trap. Using an ORM is really nice. You barely remember there's an SQL under that at all, and that's actually a problem, because the database is an external system. You should treat it like you treat an external service, like you treat an API from a service provider. Because if you don't, what happens is you do bad access patterns, you do things that are inefficient, and the ORM doesn't help you write good performant SQL. Things that look perfectly sensible in Python translate into bad SQL access patterns. Worse is that this is unnoticeable at low data volumes. Everything just works and seems zappy enough. And this happens, obviously, when you're developing and early in production. So you're babysitting your system, it seems to be doing fine, and you start to relax, everything's doing great, and then when you're actually getting some success on your system, then things start slowing to a crawl. Because SQLAlchemy is so good, and ORM from SQLAlchemy is so good that the metaphor rarely leaks. You don't see bad SQL blowing in your face while using the ORM. Things just start getting really slow. So how do you fix that? You need to be mindful of the work that the database is doing while you're operating with what looks like just Python. You need to be especially mindful of the amount of round trips that the access to your instances do, the attributes that you look up. What kind of queries does it do when you access that attribute? Is the attribute a relationship to another record? Is that triggering an SQL statement as well? You need to be mindful of those things, especially when you're looking at relationships, especially when your ORM is mapping relationships into attributes. And you should try as much as possible to reduce the proportionality of the queries that you emit during a transaction. It should be, ideally, a fixed number of queries per, for example, an API request or a background job. And you should, as much as possible, avoid looping through model instances. You have this class that's mapping to a table, and it's tempting to go to a query that pulls a bunch of those records and starts making calculations. But you should avoid that. Instead, you should let the DB do it for you. So I'm going to be talking about one case that we got in our company, which was a report that got that took more than 24 hours to run, and now it takes a few minutes. So, and for that, I need to talk a little bit about how Jira works. This is a model of how my company works that's simplified beyond any sense of closeness to reality. But it's kind of like this. There is a securitizing company, I don't know the correct term in English, that sells debentures, like company loans. With that, it acquires funds. It uses those funds to grant loans to borrowers. And as those borrowers pay back their loans, usually once a month, at the end of the month, or at the beginning of the next month, we collect everything that was paid and pay it back to the debenture holder. The contract for the debenture is such that the debenture holder knows that what we're going to do with his money, and he knows that if the borrowers don't pay, that's going to come out of his premium. So the company is not in any danger if the borrowers default. It actually is in danger of investors not wanting to buy our debentures anymore. So we have a really nice credit model to select the right borrowers. But anyway, the thing is, this last arrow down there that says pay back debentures, we run a report at the beginning of every month, collecting everything that the borrowers paid, contrast that with everything we ever paid to the debenture holder to make sure that rounding errors don't leave anything behind, or also to make sure that payments that were only registered after the last time we ran this report generate payments for things that should have gone in the previous month. So we have this kind of relationship diagram here. This kind of represents the models in our database. We have a table or a model for the debenture holder, one for the debentures it owns. So each debenture holder has one or more debentures. The arrows here indicate which record points to the ID of each other record. And then to the right side of this diagram, you have the debenture series, which is a collection of debentures that were sold to a number of debenture holders. And the loans that go out, they pay money into this account. And each payment becomes an operation into this account. So a debenture is associated also with the debenture series, which points to the account. And every month, we do a series payout. We collect everything that was paid, everything that was left behind that should have been paid before, contrast with everything that was paid, and calculate the records that represent the payment. And there is, for taxes purposes, sometimes we don't actually distribute everything immediately to the debenture holder. We sometimes create a reserve of the principal amount. so that we can pay premiums. We can pay all the principal first, and then we reserve some of the principal because the principal is not taxed. Only the premium that is taxed. So we try to pay all the principal first and pay the premium later, so that the debenture holder doesn't pay as much tax. So we have this payout reserve that we do at the end of the price of each debenture, and after that we pay only premiums, and then we pay the reserve at the end. So how does that look in code? Well, we have a base class for all the model classes, which is that class called base. It inherits, because of the SQLAlchemy declarative base call over there, from this ORM class, which has a property that makes it convenient for us to query models in a property called querying the model itself. So for example, one model is this debenture, which has a relationship with the debenture holder, like I showed before. So we also model an attribute for the relationship. And so when I access this attribute in an instance of the debenture, I'm looking at an integer. When I access this attribute, what SQLAlchemy does is it goes into the database, does a query, and pulls a record for the debenture holder, and wraps it up in an instance of the debenture holder class. And I then get access to that instance through the holder attribute in the debenture instance. Same thing for series ID and the series relationship. One important part here is this backref here. This call describes that the debenture holder class will in its turn have a debentures attribute which represents all the debentures associated with that debenture holder. And this lazy equals dynamic here means that what this attribute will be on the other class is a query. Just like model.query is, debenture holder.debentures is a query, which allows me to then apply filters and order by and things like that. And it will only go into the database to fetch records when I iterate over it. If I just access the debentures attribute in the debenture holder, I get a magical query object. It doesn't go into the database immediately. So the thing is, when this report was first running, it was taking, it had to run in two parts. One, it was going over a bunch of calculations and caching them in a MongoDB somewhere, and then running the proper distribution using these values that were cached. Why was it doing that? Why did it need to do this thing? And this caching run, it took 4 hours. And then we had like 5 debenture series already emitted, and each one of those was taking an additional 4 hours. So we had like 24 hours of reports to run this thing that ran at the beginning of every month. And people just let it there for a while because, well, you know, it just runs once a month. What's the problem with letting it run for a whole day? Well, the problem is if at the end of the report the numbers are wrong and we need to debug why they are wrong, you're facing another 24 hours of running it all over again. So what I did, let me explain this function here that I wrote in the code. So this function coalesce sum, what is it doing? It's using the sum SQL function from SQLAlchemy over a column that I pass as parameter. If there is a filter, it applies a filter on that, and I'll show the SQL of that, what it looks like later. And it wraps that into a coalesce. Why? Because sum, if you are summing over an empty set of records, instead of getting 0, you get a null. And for our calculations, we wanted a 0. So you coalesce a null into a decimal 0, when there is nothing to sum over. And if a label is also passed, this function adds a label to this column and returns this column. This is just a way of assembling a piece of a query in SQLAlchemy. And it's used in this other function here, get column sum for query, by taking a query, just like the one from model.query, or the one from a relationship, and a definition of a column. And this definition of a column is exactly the class attribute that defines a column in the model. So for example, debenture.salePrice. And it drops the order of the original query, because if we're going to aggregate, we don't need to worry about the order, and replaces everything that was in the query with a single column, which is the coalesced sum of the column that I'm interested in. What use is this? I'm going to show you it in a bit. So you see here, I imported those functions that I declared. And this is the diff of the changes that I made, of some of the changes that I made. And you can see here that what the code was doing before was looping in Python for each payback operation between a start and an ending period, and summing a few attributes of it. Then it was calculating another sum over the principal of operations, also within the same period. But you see, this is payback operations, while this is, it's payback operations as well. So it's doing two queries into the database, fetching a huge amount of records, fetching all the columns of those records, just to get a few sums, again and again. And then there's earnings operations, which is another method, but which also uses the same period start and period end, and so on and so on. And I replaced that with a method called calculate operation summary. I named it like that because just like bestiary is a collection of beasts, a summary is a collection of sums, so I thought it appropriate that since I had a bunch of sums, I would have a method called calculate operation summary. And this operation summary is a record with attributes, with names that match the variables that I had before. So how did I create this record, this one single record that has all these things, all these sums already calculated? Ignore this part for a little bit. So first off, I refactored out the method that queried the operations in a period, because you saw that various methods there were accepting start and end period, and all they were doing were filtering self.operations between start and end date, all of them individually. So I refactored that out into a method that calculates the query with these filters. And when you run this method, you're still not running the SQL. It's just assembling a query that has these filters. And I then refactored out all the rest of the filters into attributes of a nested class called operation filters. And finally, I rewrote the original methods that were using those filters to use the filters that I factored out. But I also implemented the calculate operation summary, which gets the query for the operations in the period, ordered by none because I'm just going to aggregate them all. And I replace the columns that it was going to return. Actually, it was not going to return the columns. It was returning instances of the class operation. And I ask SQLAlchemy to throw that away and instead return me the operation summary columns. You see here I use the Python operator for exploding a tuple into parameters, the star here in the beginning of the method. So, and what does this self-get operation summary columns do? It calls coalesce sum on operation value for several filters. And these filters, they are being applied not in a where clause of an SQL, but in a filter clause of a column. And in the end, because of this, I only need to return one result set. Each of those columns is looking at a set of operations, selecting some of them that they are interested in, and summing only the value of those records that it's interested in. But these records are a subset of a bigger set of records, which I'm only fetching once in the database, and asking the database to aggregate it all for me in a single step. So in the end, I get a single record, and you can see here that I pass labels here: Giro fee, earnings taxes, and those labels, they match with the attribute names of the record up here. So let's see how that looks in the code. Well, where is my... Okay. Is that readable back there? Okay. Now? One more? It's okay? Okay. So here is the same piece of code that I showed in the function down there. And one nice thing about SQLAlchemy queries is that if you print them, if you print them without iterating over them, it prints the, oh, okay, so not that. It prints the SQL query for you. So it's all jumbled up, but I have the same thing nicely formatted somewhere here. And that's unreadable. So not that. Actually, those are the slides. So you see, remember I called coalesce on top of sum, on top of the principal of an operation. One of those functions was calling operation.value, and operation.value is a hybrid property declared in SQLAlchemy that expands to a sum of other properties. So it's usable not only as a column, but also as a query, just because I declared it as a hybrid property. So the ORM is really powerful. We don't want to throw the ORM away, but we need to know how to use it to write well-performant SQL queries. So what it does here, applying filters to the columns is it filters at the column level instead of at the where level. At the where level, I have other criteria like selecting a specific dimension series that those operations belong to, and the timestamps here are filtering for the range of operations that I wanted to. But I got all those columns to do themselves their own filters so that I don't need to do many queries with different where clauses into the database. And I did that without actually having to write SQL on the Python side. I used the column definitions from the models themselves to assemble the query for me. And this was just one of the changes, and there were many other changes like this. that caused a reduction from the 4 hours of the cache plus 4 hours for each of the debenture series to 15 minutes for the run of a single debenture series. Actually, it went from 4 hours caching plus 4 hours of running reports to just 4 hours running the report, because most of the time in the second part was inserting payments, and they were inserting one by one the records in the payments, and they had already optimized that to write raw SQL inserts to make it fast, but they were still inserting one by one the records. So instead of doing that, on a second phase of optimizations, I had, let me see if it's here. No. So on a second set of optimizations, I asked SQLAlchemy itself to calculate the insert for me. Let me see if I can locate the code here quickly, because I had a little panic about 30 minutes before the presentation, because my slides stopped working, and it's like it got stuck in the first slide and it wouldn't advance, and I didn't know what was happening. But I managed to fix it in time. So anyway, before I go to that, let me show another optimization. This one brought a page that was rendering in in 1 and something minutes to milliseconds. Which was not this one. So we had this, when I think about pyramid, is that it allows you to encapsulate the logic for authentication and the lookup of the request object they're interested in the route itself. Because most of the times when you write a route in a web framework, you take the parameters and then you go look up the object, and then you check if the user that is authenticated is allowed to see that object. And Pyramid allows you to delegate this part into separate routines that are called automatically for your views, so that when you get to your view, your request object has a context object, which is the object you're interested in, and you only get there if the user is actually allowed to see that. But sometimes you also want to do permission checks manually. Actually, this admin debenture holder factory is exactly the code that's checking the permissions before the view runs. And what it was doing before, it was taking the user, taking the admin object, which is this property, it went to look up the admin role in the database and checking if it had permission to do something or some other thing. And by itself, this was already doing many queries which were optimized away when I pulled up the has permission method. But the biggest benefit actually came from telling SQLAlchemy to, when it was time to get the user, to actually load with it all the profiles, and from the profiles, load all the permissions. Because of this, the SQLAlchemy would then issue not just a query for the user, but a query for all those objects where they were joined to the user and joined to the roles, so that they were already loaded by the time the piece of code that did the authentication was going to do these checks here. So instead of going into the database to check if a user had a certain permission, these permissions were already loaded directly in memory. So I got about 10 minutes. I'm going to try to locate the code that calculates the insert to show it to you. In 5 minutes, I will open for questions. Oh, okay. Okay, so this was the final pass of optimizations that I did. And you can see here that I ripped off what was essentially raw SQL being written to insert into the database. And it was written to insert one by one each record that was needed. And instead, I asked SQLAlchemy to generate the inserts for me. Because when you look at the model declaration, the model declaration, it has a dunder table attribute, which maps to the DSL for writing SQLs that SQLAlchemy has, and then you can ask it to do an insert, to return to you the query that does the insert. So here we have it. A payout insert is a debenture payout.dundertable.insert. And the insert method has a from select, which does an insert from select, and you pass it the list of columns that you're inserting from the query, the names of the columns, and you pass the actual columns or constant values or whatever you need to insert into the database. So instead of looping on Python side, inserting a lot of objects, I asked Postgres to loop on his own side over the objects that he knew existed and insert values calculated according to what I needed, so that I didn't have to insert on my end each one of the objects. So that brought down the whole report from 4 hours down to 15 minutes. The other optimization I showed before, the one about authentication, there were some pages that were taking over a minute to render, and they were rendering down to a few milliseconds. So going back to our message, in order to write good performing ORM code, no matter how comfortable the ORM code is, you need to understand SQL, even if you're not going to write it by hand. Even if you're just using the DSL from SQLAlchemy, it's already a really good way to refactor the common parts of generating SQL. But you need to understand what the database is doing when you access an attribute, or when you do an insert, or when you access the attribute of an attribute of an attribute. And you should know how to do things in a well-performant way in SQL, so that you can map that to idiomatic SQLAlchemy. So I recommend highly that you read the select documentation for a database and try to understand which part of it does, and look up in Stack Exchange what does it mean, how group by interacts with aggregation functions to reduce the number of rows that you get back, and why you need to have a column either in the aggregate or in the group by clause. Understand the window functions of SQL, which is another way of calculating aggregates without reducing dimensionality. Read about subqueries and with statements that allow you to calculate a part of SQL, then calculate another part based on that calculation, all going in a single round trip to SQL. And then you study SQLAlchemy and understand the underlying queries that SQLAlchemy is generating when you do attribute accesses. Try to push as much work as possible into the DB, but not too much. Sometimes you're going to be generating a very complex query, and it goes only one time to the DB and brings a bunch of information, but then you don't need all that information. Be careful of the amount of information you need. And if for some reason you're bound to a loop on the Python side because you need to do some Python calculations, doing a very complex SQL query before entering the loop is kind of useless. So you might have to do a few round trips to the database, but be mindful of the queries that you're generating and try to reduce the amount of queries that you're doing and the amount of volume of data you're trafficking. And that's it. Thank you very much for your attention.
Thank you, Leo. If anyone has questions, they can come to this microphone and ask them. I request that you keep the questions objective, and if you have more detailed questions or want to or comments, please see Leo outside in the interest of time. Thank you.
Thanks for the talk. I guess when we do optimizations, nothing comes for free. So you bought yourself a lot of speed ups. What do you see as the costs of the optimization? Like, well, what did it cost you? And I guess if you have time, there's a second question, which is, did you ever consider giving up on the SQLAlchemy DSL and just writing SQL as strings? Thank you.
I did, but most of what I needed to do, as I showed you, were trivial changes from summing on the Python side to summing on the DB side. So there weren't that many things that were that complicated. I was lucky that I knew about the filter where clause for columns that allowed me to do a single round trip to the database. And when I showed that to my colleagues, they kept asking me, how do you know about this? How do you know about this? And it was pure luck. I'm curious. I was reading the long before doing this optimization, I was reading the select manual from Postgres, and I was curious, oh, why does it have a filter where here? And then, oh, that's what it's for, and things like that. Unfortunately, there isn't much documentation, either on Postgres or on SQLAlchemy, on why certain things exist. They are there. If you're looking for them, it's easy to find how to do something. But if you're not, you have no idea what to do. So my tip is always study what the select can do, what insert can do, what update can do. Go into the little corners. What does window mean here? What does over mean here? What does filter where mean here? And trying to find examples of these things working so that you have baggage to optimize these things later. And then I had not much difficulty in convincing SQLAlchemy to do those things in a Python idiomatic way. But the point is, the Python idiomatic way without thinking about SQL is going to lead you to generate bad SQL. But if you are aware of it, it's easy with SQLAlchemy to generate good performant SQL from idiomatic Python accesses.
Do you have a favorite way to review queries when they come out? I saw the text blob up there, and I've had a similar problem where it's like, oh, great, it gave me this query. Now I need to format it in such a way I can actually read it. Do you have a tool or a script you run for that?
There is a Python library called SQL format that you can run it through. There is a Perl script called PG format that does that as well. The query that I showed was formatted with PG format, actually. So talk to me later, and I'll show you the URLs for those.
Excellent. And I had one more question, that filter on column. I found that interesting, too. How do you do that in SQLAlchemy? What's the call to that?
How to do filter where?
Filter on the column as opposed
yes,
to on the query.
you just do a column. If the column is an aggregation, like a sum or something like that, it will have a filter attribute. So you do sum of my column, or average of column, or count of column, func.count, func.sum, close parentheses, dot filter, and then you pass the same things you would pass into a filter clause of the SQL.
Excellent. Thank you.
Hi. Great talk.
Thanks.
I have a question about where you decided to do your optimizations. How did you identify that you needed to optimize that particular query or that particular function? Did you do that through manual code review? Did you use some sort of profiling library in Python? Or did you review the SQL queries running on the actual database and then traced it up that way?
Yeah, actually, there's something that I realize now that is missing from my talk. I should have emphasized how important logging is. So if you configure the logging level of SQLAlchemy to info, it will show all the queries. And then if you're running a report and you're getting spewed on by gobs and gobs of queries, you know there's something there that should be optimized. I also use, well, if you're using some service like New Relic, you usually nail down, for example, in the case of the authentication there, it will show, oh, this function here that's doing these queries is being called a lot. But also there's a WSGI filter called SlowLog that dumps tracebacks of your request if you're using a web framework that's written on top of WSGI. You can use SlowLog and point it to a file, and every request that takes more than, say, 2 seconds, it starts dumping every second the traceback of that thread. So if you see that you're hitting SQL a bunch of times, you say, oh, either this query is very, very slow or this query is being called a lot. So you know how to optimize it just above that. But that's mostly it. Of course, nowadays, I see a sum over an instance of a model. I ask my people on my team to rewrite that. So it's like, please don't sum on the Python side.
If we don't have any questions, thank you so much, Leo.
Thank you.